Hello everyone. Welcome to the video introduction of our ICCV 2025 paper on light field super-resolution with Hello everyone. Welcome to the video introduction of our ICCV 2025 paper on light field super-resolution with spatial-epipolar implicit image function. Existing light field super-resolution methods mainly rely on CNNs, transformers, or even Mamba models. These works have indeed advanced the field, but they mostly focus on the encoder. In contrast, the upsampling process in the decoder is often overlooked. As you can see in the figure, current approaches usually apply transpose convolution or pixel shuffle on each subaperture image. This simple operation ignores the underlying 4D geometric structure. For example, it treats each subaperture image independently and only performs naive spatial upsampling, without considering the correlations across different views. Moreover, these methods lack flexibility. In real-world applications, the desired upsampling factor is not always fixed. It can vary depending on the device, the display, or the specific task requirements. However, once the scale factor changes to a value that the model has never seen during training, these networks fail to generalize. In other words, the well-trained model becomes invalid and can no longer produce reliable or high-quality results. This limitation makes existing methods less practical for flexible and adaptive light field super-resolution. Recent methods have shown that by using implicit image functions, a model can directly predict RGB values at any coordinate in the high-resolution space, and this enables arbitrary scale super-resolution with impressive visual quality. Motivated by this, one natural idea is to simply transfer these methods to the macropixel representation of light fields. However, this doesn't really work because MacPI takes macropixels instead of individual pixels as the basic elements. That means pixel-based implicit functions cannot directly generate continuous macropixels for light field reconstruction. Alternatively, if we apply implicit functions to each subaperture image, it becomes feasible. But this strategy ignores angular cues that are crucial in light fields. Another option is to use the epipolar plane image, or EPI, as a representation. Since EPI is still pixel-based, implicit functions can be applied here, and using implicit function on EPIs can capture angular clue. This figure is the overall workflow of our proposed SCF. SCF is inspired by spatial angular separable modeling. In SIF, our goal is to learn a shared spatial implicit image function, which uses spatial context from a single view to predict pixel values at arbitrary 2D spatial coordinates. To achieve this, the feature vectors are first reorganized into a 4D tensor. To align with the upsampling step in the EIF branch, SIF is implemented in two upsampling steps. Features are firstly generated by upsampling horizontally, and each query coordinate is processed using the nearest feature, relative position, and cell information through a small neural network. Features are then upsampled vertically, combining information from both steps to predict the final high-resolution pixels. This two-step approach allows joint optimization with the EIF branch, fully capturing both spatial and angular correlations. Compared to one-step upsampling, it leverages the 4D structure of the light field more effectively, resulting in more accurate high-resolution reconstruction, while SIF focuses on capturing latent representations within a single view. We introduce EIF to complement it. EIF learns an epipolar image function to exploit the interview relationships encoded in the line structures of epipolar plane images. The EIF branch works in two upsampling steps. First, horizontal EPI upsampling. The feature vectors are reorganized into horizontal EPI patterns. Instead of simply using nearest neighbor sampling like in SIF, EIF employs a spatial sampling strategy designed to capture both visual features and coordinate information along the EPI lines, even under varying disparities. The sampled features, combined with cell information, are processed through a small neural network to generate intermediate features. Second, vertical API upsampling. The intermediate horizontal features are then reorganized into vertical API patterns. The second step maps coordinates to pixel values instead of intermediate features, producing the final high-resolution output. By combining spatial context from SIF with the epipolar features from EF, this two-step process fully exploits both within-view and cross-view correlations, leading to accurate reconstruction of high-resolution light field images. Previous works usually predict pixel values by aggregating information from neighboring pixels. However, this approach is not suitable for APIs. In APIs, the effective information that is, the spatial angular correlation lies along line structures, not just in a local neighborhood. To address this, we designed an oriented line sampling strategy to correctly capture interview information in APIs. Let's take a horizontal API as an example. The workflow is as follows. Line structures in an API can have different slopes depending on the disparity. The first step is to determine the epipolar line where a query coordinate is located. This is done by computing feature differences rather than color differences, because the feature space can capture more comprehensive pixel information. We predefine a set of slope candidates and, for each candidate, select three coordinates nearest to the query along that slope. Then, we sample the corresponding feature vectors and compute the variance among them. The slope that gives the smallest variance is chosen as the correct epipolar line. Finally, the three sampled features along this line are concatenated with relative distance information and fed into the neural network. This becomes the final input of our oriented line sampling strategy. It's important to note that using more than 3 samples along the line is not necessarily better. More samples increase computation while giving only marginal improvement in accuracy. Additionally, occlusions can break the integrity of the line, and more samples in such cases can actually hurt the result. Therefore, we use 3 carefully selected samples for each query, which balances accuracy and efficiency. To train SEIF to generate continuous representations for light fields, the training strategy randomly samples an upsampling factor in each iteration. Importantly, in a single batch, both low-resolution and high-resolution samples share the same factor. This table shows that SEIF achieves comparable or better performance than existing single-image super-resolution methods. In particular, SEIF outperforms other methods not only on standard upsampling scales, like ×2, ×3, and ×4, but also on larger, out-of-distribution scales, such as ×6 and ×8. A key advantage of SEIF is computational efficiency. Unlike CHO-SR, which uses an attention-inattention framework and requires massive flops, SEIF can handle larger upsampling factors in real time. Although SEIF is slightly slower than DIF due to looping over multiple candidates in the oriented line sampling, this trade-off is minimal compared to the gain in accuracy and robustness. For the fixed scale task, there is an additional fine-tuning phase where the upsampling factor is set to the target scale. Using SEIF in the decoder consistently improves the performance of all methods across almost every dataset. On average, the PSNR improvements range from 0.12 to 0.39 for 2 times task and 0.23 to 0.51 for 4 times task, demonstrating the powerful decoding ability and strong generality of SEIF. Here, the figure shows a comparison of 4 times light field super-resolution results. The top row uses the original upsampling modules, while the bottom row uses our SEIF. As can be seen, with SEIF, all methods significantly reduce blurry textures and produce much sharper, clearer images. Here are qualitative results of SOTA methods for arbitrary scale tasks using dist-SSR as the encoder. Here are qualitative results on the same scene with diverse scale factors of LTE, DIF and SEIF using dist-SSR as the encoder. Ablation experiments are conducted on benchmark datasets, using disk SSR as the encoder, and PCNR is used as the default evaluation metric. The top table shows SIF and EIF contributions. 3 variants were tested, 1 without SIF, 1 without EIF, and 1 without interaction. The results show that both interview and interview information are beneficial for upsampling. Notably, removing SIF has a bigger impact than removing EIF, indicating that interview information plays a major role. If SIF uses simple one-step upsampling, the 2 branches become independent and cannot fully integrate interview and interview information. In this case, PCNR drops slightly, showing that joint feature interaction between SIF and EIF is meaningful for accurate reconstruction. The middle table compares different sampling strategies, show that OR-oriented line sampling effectively captures interview correlations along epipolar lines, leading to higher PCNR. In contrast, naive local sampling or attention-based weighting either worsens performance or increases computation unnecessarily, proving the effectiveness and efficiency of our design. The bottom shows the role of training strategy. For fixed-scale tasks, SCIF is first trained on multiple discrete scales to learn a general super-resolution rule, followed by fine-tuning on the target scale. This two-phase approach enables cross-scale knowledge diffusion, significantly improving PCNR across all scales. For arbitrary scale tasks, uniform continuous scale training performs poorly because the angular correlation across views varies with scale. Limiting training to several discrete scales allows SCIF to learn robust spatial and angular representations, achieving high performance on both in-distribution and out-of-distribution scales. Overall, experiments with different encoders and decoders confirm these findings, showing that SCIF consistently achieves high-quality reconstruction, robust generalization, and strong decoding ability, especially for larger upscaling factors. In this work, we introduced the Spatial-Epipolar Implicit Image Function, or SCIF, which provides a novel perspective for light field superresolution as a universal upsampling decoder. SCIF can be applied after any light field encoder to enhance performance. Beyond that, it is capable of learning continuous light field representations, enabling arbitrary scale superresolution. Both quantitative and qualitative evaluations demonstrate its strong capability and robustness. Looking ahead, we plan to explore better implicit light field representations and develop more efficient architectures for the decoding process, aiming to further improve performance and efficiency. Thank you for your listening. If you have any question, feel free to contact us.